And here we go. Share. Okay, so I hope you guys tried this problem, because this is going to be a typical problem that you're going to be getting on the exam. And at the same time, it's not just the fact that it's for the test, but for your own knowledge on how to do this, if ever. Okay, so here we had a simple using M22 bolts. Okay, so in other words, I'm giving you the diameter of the bolts. And of course, this is the strength of the bolts. As you remember, there's A325. That's the more typical one. And I should have put an M here because I'm using metric. That's the right way of doing it. And then there's the A490. They're both considered high strength bolts. This one is a little bit stronger, and this is the more typical one. Now you determine if 3 bolts are sufficient. In other words, the reason why I do this, because this way I'm giving you some fixed geometry here, okay, so that I can see if in theory, you would have to decide on what the end distance is here. What is the, excuse me, the pitch between the bolts and the end distance of your gusset plate. This is something you'd have to determine. And these are pretty much, like 80 and 80 is what you normally do. And of course, because of the gusset plate, you want to make sure that you have sufficient resistance in the gusset plate and all that. So now, the size, okay, the size of the angle, the thickness of the gusset plate required to the threads of the bolts are excluded. So that means you can use a higher value, and the shear planes, and the holes are punched. That means that you have to make an allowance of 4 millimeters. Okay, you have to make an allowance of 4 millimeters for the bolt holes when you're doing your calculation. The steel, the angles are 350, okay, and the angles, now here I'm giving you, for example, I'll give you 2 of the 3, and then you just go on the table and select the one that you want to design with. And I do that because otherwise, with 35 students, I'm going to have 35 different choices. So I'm doing this so I can narrow it down, okay? But in reality, you would have to go into the tables and find an area that you want to start with as a preliminary, as a preliminary size. So that's the only reason why I'm doing this here, so that I can narrow down the number of choices that you guys can make, okay? So here, all I want you to do is determine the size of the leg. And okay, so here, and the long legs, so here when I say the long legs are back to back, what that means is that, okay, this is the angle here like this. Okay, so the long legs will be back to back, okay? And of course, what you have to remember here is that if the bolts are going across here, okay, that you have, what you have to remember is that you have one shear plane here, and you have one shear plane there. So therefore, the bolt can be resisting at 2 different locations. Therefore, you can take the resistance of the bolt there and the resistance of the bolt there to give you the total resistance that the bolt is going to offer to the connection. And normally, we put the long legs back to back if it's tension members, believe it or not. And if it's compression members, we put the long legs outstanding in compression members, and we put the short legs back to back, because the further this is away from the from the centroid here, the more resistance these angles have. So depending on whether it's tension or compression that these members are going to be subjected to, that's how you determine whether you're going to be putting the long legs or the short legs back to back. That's just for your general information. Now, oh, sorry, let me just do the slideshow. Okay, so here we go. Now, so what you do is we said M22 bolts, okay? So we're gonna go to this table here, M22 bolts, and we said that the threads are excluded, and therefore we know for an A325M, like I said, I forgot to put the M because of the metric. Okay, each bolt per shear plane can resist 151. So this table is kilonewtons per bolt, okay? And that's what we get from here. And that's where we get that value. So we get, so here we say 151 kilonewtons per bolt and shear plane, and therefore we have 3 bolts and we have 2 shear planes. And I showed you that before, why we have 2 shear planes, because each angle is creating a shear plane. And in this case here, we have 906, which is greater than the 900 kilonewtons. Therefore, the bolts would be sufficient to resist the force that it's being subjected, the connection is being subjected to. So now that you're satisfied that the bolts are okay, the next thing to do, 3 M22 bolts are sufficient. Now, what are the modes of failure? So, okay, the first one you worry about is, of course, the whole, the members themselves will fail, okay? So basically what you're doing is you find a TR value for the member failure. And here you're saying that this TR value, of course, has to be greater than the TF value here. And therefore you find what your AG has to be in order to satisfy your first section failure. And we end up getting 3,333 square meters. Now we know that because these angles are only connected on one leg and are not on two legs, there's going to be a shear factor, okay, a shear lag factor that's going to affect the resistance of the connection. And therefore, we're going to make an allowance for shear lag. And if you remember what shear lag is that it kind of, it kind of compensates for the fact that you have concentrated stress in one area of your connection, and by the time they become uniform, it takes a certain amount of time for them to become uniform, and therefore you're compensating for those concentrated stresses around, around the bolt holes. Now, here we know that for they recommend for shear lag that you use a value of 0.6 that I gave you in the table. And therefore, you're looking for an area that's approximately, okay? Now, if you go over this, you're going to be very conservative. If you go slightly under, it might still work if you can find a value. So this is just to give you an idea in which range you should be looking for your AG. Okay, which range you should be looking for your AG, and therefore, so what we do is we go, okay, so we're looking for at least, what was it, 5,000 something. And if I'm not mistaken, I told you to take a blank 102 by 11. So you're looking at somewhere in here, blank 102 by 11. Okay, don't forget you have 102 here also, and so on and so on. And you have the 11 there. So you're looking for an area, okay? So this here is okay. This here is also okay. This is higher. So this would be a little bit more conservative. And of course, here there's none. So therefore, I'm going to try as a trial section, okay? And of course, so I'm going to try this one here, 152 by 102 by 11, because it has an AG of approximately of what I need, and therefore I'm going to use the 5390, 5,390 square millimeters, and see if that works for all the conditions and all the possible failure planes. So I'm going to use it gives me 5,390, which is around the area that I need, okay? And like I said, if you find something very close to it, the closer it is, and if you go above, most likely everything's going to work properly. So that's going to start with, I'm going to start with these angles here, and I have an area of 5,390 square millimeters. Now, failure plane number 2, failure through the first transverse bolt holes. What I'm saying here is, like you have your angle here. Okay. And of course you have the one behind it, right? And we have a hole there, okay? And we're assuming that, like, we've already checked this here. This we've checked, and we know that we're okay because we only need whatever was 3,333, and we have 5,000, so we have no problem there. So this was really number 1 here, okay? And this is number 2. So what you're looking at is you're asking yourself, okay, you're going to be removing that amount. You're going to be removing that amount of of the material to make the bolt hole, and therefore what we're saying is the TR equals phi u ANEFU, and therefore you find the AN value. So you take the total gross area of the angle and you just subtract 2 holes, because that's what you're left. In other words, where the failure plane is going to happen, it's going to be, like you just remove whatever the material you need to remove to create the bolt holes. And of course here what we're saying is It's an M22 bolt. Since we're assuming that they're going to be punched, we have to assume that the hole eventually will be 26 millimeters. This is more for allow for the deformation caused by the punching. And of course, the thickness of the legs is 11. Therefore, the total material that is removed to make the 2 bolt holes, subtracting it, because this is the area of both angles, that will give me the net area. And now we have, so we have AN is now, to account for shear lag, what we need to do is, of course, multiply. In other words, A and E is to account for shear lag. This is your net area, therefore we multiply by 0.6. And we drop down to 2,891. Now people say, well, if the other one is 3,333, why is this one lower and it still work? Because here we're using FU, we're not using FY. Okay, that's the difference. Is that in this equation we use the ultimate tensile strength, whereas in the other one we use the ultimate, we use the yield strength for the other equation. So now we have that. Of course, we can just put into the equation 0. This is the value, the reduction factor. And of course, we end up getting 975, which is, so therefore we know that it wouldn't fail there. Now, the other possible failure plane is the block shear. And I found some pictures I'd like to share with you if you remind me. I have to go open them up, but I found some pictures and I can show you some of these block shears that they actually do happen and some failure planes that actually happen from one of the files that I worked in the past. So if you guys remind me of this at the end of the lecture, I'll be more than happy to go open the pictures and we'll take a look at them together so that you can get an appreciation that when things are undersized, they do fail, okay? And so what is the block shear? What I mean by block shear is, of course, in this case here, I have my angle here like this, okay? And keep in mind that you have 2 of them back to back, okay? And you have 1, 2, 3, and what you're actually looking at, okay, you're looking at this and this breaking off. Okay, so that's what it's called a block shear. Okay, and in that case, you got to use the second equation. So this is the equation we use, and of course, this part of the equation here is all for here. In other words, it's just for this, the little resistance or the resistance offered, because here the steel is in tension. So this part of the equation here is for here, and this here is shear. And therefore, this part of the equation here is for all the resistance offered by that section of the failure plane. Okay, so this is for the tensile part, and this is for the shear part. Oops. So now, of course, what I do is I simply take the length of the leg, which is 152. I subtract where the bolt hole is from one edge, okay? And then I take 1/2 of the bolt diameter. So all I'm doing here is simply this, okay? Here is, okay, okay. So I got 152 here. Here's the, okay, so I got 152 going across here. That's the size of the leg. And I left a 45 millimeter distance between the edge and the thing. And then I'm just going to subtract, okay? So it gives me what's left here. That's all I'm doing here. So mathematically, since I'm going from, that's the area that's in tension. So I'm taking 22 plus 6, which is 26, minus 1/2, and times 2 angles. And that gives me my AN right there for the 2 angles, which gives me 2,068 square millimeters, which is significant. And then after that, for the second part, okay, what I do is there's 80 millimeters between the 2 holes, and this is the end distance multiplied by the thickness of the leg. And of course, I've got 2 angles. That gives me the amount of area, gross shear area that I have in my connection. And in this case, I got 4,180. Now that I got both of those, I simply put everything here. And now in the utility factor, if you remember, I gave you a table. They're saying that when the utility, okay, here, this was 0.6 when you have angles that are only connected on one leg. And this is the AN you just connected for that, and so on. And of course, don't forget, work everything in the brackets first and then multiply by 75. Typical problem is that people do this and then they add that to it. They forget to reduce this by 75, by 25%. Typical, mistake that people do. So all of a sudden I get 1,124. I agree in my TF. Perfect. I'm okay. I know that that's going to be even a little bit more resistant than going through one hole. So now I can check the bearing, okay? And of course, the bearing here is I have, what do I have? I have 11 millimeters of thickness of the leg, and I have an M22 bolt. So for bearing, this is the thickness of the material. This is the size of the bolt. So therefore, and of course, this is the right steel, okay? Therefore, I have 261 kilonewtons of bearing per bolt, okay? So I have 11 M22, 261 kilonewtons per bolt. And of course, I have 3 bolts and I have 2 angles. So therefore, I have a total of 6 holes that is bearing, okay? And in this case, I get 1,550 fixed, which is greater than my TF. So I know that there's sufficient bearing between the bolts and the angles. Now, the last thing I need to design, of course, is the gusset plate. So the gusset plate is basically this equation here with this thing going to 0. In other words, in your gusset plate, all you're going to have is, of course, I'm trying this from memory, guys. Okay, I'm going to have 1, 2, 3 holes, and therefore I'm just going to, it's going to have to shear along these 2 sides. Okay, and therefore I'll be able to calculate the AGV required. Okay, based on this length I've determined by my geometry, and I leave everything in terms of T, and therefore I can calculate what the thickness of the plate has to be in order for it to be sufficient to resist the forces in the connection. So AN is 0, there's nothing in tension, everything is in shear, and of course this has to be greater than 900. So I have 80 times 2 plus 50, because that's the end distance, times 2. The 2 here, as I should have left a little drawing here. Let's see if I do it, Control Z. Yeah, like in other words, the reason why I say 2 is I have 1 here and 1 there. Okay, so that's 2. Okay, and then T. And that's why I have a 2 here. So I end up with AGV in terms of T. And of course, now I have all the other variables for this equation. I know what Fy is, I know what Fu is. So therefore, I simply substitute all the values in here and I calculate the value of T. I get 12.7. And of course, there's no such thing as a 12.7 millimeter plate. So you go to you come here and you look at something that's greater than 12.7. So you can use, you can use a 14 millimeter, which would be your second preference, or you can simply say 16 millimeters. Like you don't have to put 14. You can specify 16 because that's your first preference. But if you want, you can specify 14. It's up to you. But you know that they do produce 14 millimeter plates. If the guy has some 14 millimeter plate in his shop and he wants to use it, by all means, but he most likely is going to have a 16 millimeter plate, so he's simply going to put 16 millimeters when he fabricates the the connection. So 14 millimeters second preference, 16 millimeters first preference, and of course you got to always check the bearing. Okay, so in other words, here what happens is that, again, I'm going to draw this properly so you guys can see what's happening. Okay, so oops, sorry, I drew this a little bit off here. Okay, so what's happening here? 1, 2, 3. Okay, so where am I? So as the angles want to pull out of here, okay, what's going to happen is the force is going to be going here, and you want to make sure that these things don't deform. Okay, this is where the bolts are bearing on the gusset plates. Okay, so therefore you want to make sure that the BR here can resist. Okay, the sum of this one and this one and this one can resist the 900, okay, kilonewton force being pushed against that surface hole of the gusset plate. That's what you're trying to do. And now, so you go to, we'll go to see what happens with a 14 millimeter plate. So this is what the bearing is for a 14 millimeter plate, and it's bearing with on a 22 millimeter diameter bolt. And guys, I hope you appreciate that. As the bolt gets bigger, so does the surface area that the bolt is bearing on that surface area. And of course, the bearing should be going higher and higher as the bolt diameter gets bigger. I hope that's something you can realize. And therefore, I said here for 14, I end up with 333 kilonewtons per bolt. Okay. Now here, contrary to the double angles, we don't have 6, we only have 3. We only have 3 holes that are, so I have 333 kilonewtons per bolt, okay, and I only have 3 bolts in this case, so therefore I multiply that by 3, I end up with 999 greater than 900, so my bearing is okay. So therefore, my connection would be sufficient to resist that 900 kilonewton force that is being subjected to, both for the angles and for the gusset plate. Now, what we're going to learn eventually, if we need to do this, okay, is if you want to weld your gusset plate to something, we'll learn. We're going to start learning about welding today. So, before I leave here, does anybody have any questions? It's all clear. It's all good.
Yeah.
Okay, if it's all good, then we'll close this and we'll talk about welding. So we'll close this. Okay. Okay, now, guys, like I said, the 2 typical, like the 2 typical elements that we use to connect steel is bolts and welds. What do you think we used to use in the older days, other than bolts and welds? Does anybody know what type of element we used to use to connect steel in the, let's say, in the 30s, 40s, let's say pre-1950?
Rivets.
Rivets, okay, guys, rivets, okay? And I mean, it's interesting, okay? It's interesting because rivets are actually heated up, okay? And then they're banged into place to get that rounded head. So rivets, okay? So, and believe it or not, so if ever you need to do some analysis on an existing structure and it's got rivets, well, it's doable, but there's it's interesting. I've done some for myself, and I've learned a few interesting things about rivets that you have to allow for them. So we'll talk about welded connections, and of course, hold on a second, annotate. Yeah. So we are going to. Okay. Now, welds. So first thing I want to do is give you an idea of, okay, common types of welds. Okay, so here are, for example, these are the symbols that you'll see. Okay, these are the symbols. Okay, and okay, so these are the symbols. And this, so when you talk about a square butt weld, that means that the surface of the material that you're welding here is square. Okay, so that's what that means. And then of course, and then this is how the surface is prepared for the welding material to be able to fuse these 2 elements together. So you have a V, you have, okay, single bevel. So in other words, these are all, so whenever you want to have a complete welding of one side to the other, okay, so these are what we call full penetration welds, okay. And of course, when you're going to have two elements that are going to be like side by side, okay, this is the most common type of weld that we tend to use, okay, it's called a fillet weld, okay, in other words, this is what we're basically, so for example, if I have a steel angle here like this, okay, if I have a steel angle here like this, and I have a plate here, okay, the most common way of welding this together, okay, the most common way of welding this together here, around here, okay, is to use what they call a fillet weld. And what it does is that it looks like this, and therefore it kind of fuses this surface and that surface and connects everything together, okay? And of course, now if you don't, this is just a weld, you can have it on both sides and so on and so on, okay? Now, this is also sometimes used, a plug weld, for example, if I have a big plate here like this, okay? And I have another plate here underneath like this, okay? And all of a sudden I want to, I make holes here in this plate, okay, just in one plate. And then I fill this up. I fill this up with the welding material. So this is called a plug weld, okay? And then, of course, you can have just a touch here and there, and they call those a spot weld, okay? Now, just so you can differentiate, they don't talk about it here, but okay, when you're welding that steel deck to your framing of your roof, okay, that's just called a puddle weld, okay? It's a puddle weld. It's not even called a spot weld. They call that a puddle weld. If you want to call it a spot weld, I guess they're just as accurate. And of course, these are symbols to show you, you understand, how the profile of the weld, so flare bell weld and so on. So if ever you see square butt weld, this is what you're supposed to be seeing. If you see the symbol, that means that the two surfaces are going to be cut at 90 degrees. Now, for example, when you're, when you're joining pipes together, in a pipeline, okay, those are all welded completely from one side to the other. And sometimes, like, it's very, very, you understand? Sometimes they might even do this, understand? Just leave a little bit of a root there and a little bit of a root there, and so on, and then they're going to make sure that this is completely welded. Okay, so this assures that the member, the one side of the member is completely welded to the other side. So that's where you see most of these when you're welding pipelines and stuff. Okay, and of course, when you're talking about structural steel and you're putting two elements together, this is the most common one that you see. Okay, so that's just to give you an idea of like and guys, just to let you know, okay, there are people that make their careers. They're called welding engineers. All they do is they get involved in welds, believe it or not. Okay, so that's how vast just this one area can be. Okay, so for example, they make a career out of welding. Okay, so they can be hired by pipeline companies, they can be hired by structural steel companies, and so on and so on. And they get involved on making sure that the quality control and everything meets the specifications. So. And what we're going to be learning today here is going to be like, very, very general, very, very general information about welding. But man, you can really go deep into welding. Okay. And as a matter of fact, you can make a whole career just out of welding. So now, welding symbols. Now, this is going to look a little complicated, but then I'm going to show you some more examples where you'll be able to relate to it a little bit more. But these are the welding symbols that you would see on a drawing. Okay. So for example, this is a symbol that represents that you want a fillet weld. This is a plug or slotted weld. This, if you want that square one that you saw before, this is how you're going to prepare the edges of what you're welding. Okay, so this, we saw that before. And these are the other symbols that you see. So this is for the preparation of the surfaces where the weld is going to be performed. Okay. And this, there's no surface preparation. You're just going to be plugging and then this is the fillet weld. Now, this is a symbol that represents you weld all around. In other words, everywhere that there are at least two surfaces that have to be welded, you're going to weld that whole perimeter of those surfaces. This means that you're going to be welding in the field. Okay, and then you're going to see how this is applied. And of course, this tells the guy whether you want, after the thing is finished being welded, okay, after the thing is finished being welded, do you want it to be convex? Do you want the weld to end up looking like that, or do you want the weld to be flush? So this you tell the guy, because if you want it to be flush and the guy happens to make it like that, then you'll have to grind it down. They just simply grind it down and make it flush. If you want it convex, then the guy's going to make sure it's got a little bit of a bow in there. That's just how the weld is going to end up here. So these are the symbols, and on the next page you're going to see how this applied to a drawing. Okay, and so we're going to talk about these especially because this is the most common weld that we're going to be using in our connections, and we're going to be talking about these symbols here. Okay, and how you apply them. And as far as surface preparation, you won't have to do any. Okay, so this is how you show it on a drawing. It looks very, very complicated, but don't worry about it. Okay, so here, what you're doing is you're pointing to where you want the weld to be performed. Okay, the arrow connecting, reference line to the arrow of the joint also points to the groove member in the bevel. Okay, so this points to where you want the weld to be performed. Okay, now if all of a sudden I have here a plate and I have another plate like this, right? And I want to connect these together and I want to make sure the weld goes all the way around like here. And then of course, also on the underside here, okay, then I would put this symbol here. In other words, just weld all around. That's what this means, okay? And it would even be on the underside here. So you want the guy to weld here, 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 all around. And if this has to be performed in the field, of course, you're gonna say weld in the field because guys, you try to minimize welding in the field. You try to weld everything in the shop and you try to bolt everything in the field because welding in the field is about 3 to 4 times more expensive than welding in the shop. So whenever you see connections, you're going to decide what you're going to be welding in the shop. And then once you weld it in the shop, you're going to be bolting everything in the field. So this is used under very special circumstances where you have no choice but to do the welds in the field. And when you're welding in the field, guys, welding is a very, very delicate operation. It all depends on temperature, this and that. So you got to be careful about that. Okay, so this is, I mean, it is used. I mean, sometimes you have no choice because, that's the only way of doing it, welding in the field. But if you can avoid welding in your field, you do so. You make sure everything is welded. Now, this here is the length of the weld. Okay. In other words, if I put 150 millimeters, that means the segment is going to have 150 millimeter length, and this is the pitch. Okay, in other words, if this, for example, I have a long, you'll see this on the next diagram. If I have, for example, I wanted, 150 millimeters there and leave 100 in between, then I would put 100 here, and that's the pitch. So therefore, that's how you would specify that you weld 100 millimeter segment there, leave 100, 150 millimeter there, leave 100, because you don't necessarily need to weld the whole thing because it would be too much, okay? And even at 150. So this is the length of the weld, this is the pitch. In other words, the distance between the weld segments, okay? Now, when you're pointing here, for example, let me clear this. Okay, so for example, here I have, okay, like this, okay, and I have a plate there. So I'm pointing here, okay. Well, if I put at the bottom, this applies to this side of that connection, okay. And if I put something else here, it applies to the other side of the connection. So it's got to be, you got to be very careful on which side you put the symbols, okay. So that's why, so normally you're going to see it on the next page. So therefore, if I'm pointing here, I'm pointing to where, like this is, okay? So in other words, both sides, okay? Or if I'm pointing here, because on my drawing it's not clear and I want it to be on the other side, I put the information above. So guys, these are very, very, important graphics when it comes to welding. And therefore, if you want to be sure that the guy reads what you're telling him to do correctly, this is what you have to make sure you're doing, okay? Now, number of spots and projections and all that, okay? Now, this here, I never get into it. This is where you get some very sophisticated type of welding, there's specifications and so on, and okay, for surface preparation and okay. So basically what we're going to be worrying about, like what I worried about most of my career is simply this, 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 and of course pointing to the weld. Okay, the other stuff is like when you start getting into some very, very sophisticated welding procedures and all that, then you want to make sure that the that the that the welder follows your procedures to the T. Okay, because normally, you know, you leave it up to him. Okay, so that's the, and now you're going to see how this applied to a drawing. Okay, so this is, like I said, it's very, here to giving you the full range of how you, like, this is a complete weld specification. Okay, almost. Okay, so, and now we're going to see how this is applied in reality here. Okay, so here, so you have metric measurements and imperial measurements. Now, of course, metric, you talk millimeters, imperial, you talk inches. Okay, so here, for example, a double fillet weld, okay, in other words, if I put this here, that represents, remember the symbol for a fillet weld looks like a little triangle like this, okay? And of course, you don't see this part here because that line is there. This gives you the size of the weld, okay? And that means that from here to here, you have 6 millimeters, okay? So here, what this means is that where the weld is pointed, I want an 8 millimeter weld. And on the other side where you're going to be welding, I want a 6 millimeter weld. So you can specify two different weld thicknesses if you don't need to have, okay? And of course, like I said, this is for the specifications. I never bother with that, okay? And this gives me the length of the segment. In other words, this would be 300 millimeters long in this case, okay? So that's how you would, you know, like, and of course, now, in imperial, so this is what you see. For example, if you see here, and for you to be able to relate it, if I see this, I see this symbol here, that means it's a fillet weld, okay? Because it's really, it looks like, in other words, it looks like a fillet, right? And I'm pointing to this side, therefore everything has to happen on this side of the connection, okay? If I happen to want to also weld on this side, then I would have to have it also above. And I only point to one side, just like you see here. Okay, so this means is that this is the length of the weld. Okay, and this is the pitch of the weld. So in other words, here what you want is you want 2-inch length segments and spaced at from center to center 5 inches. Okay, now here you see the same thing, except that here they're doing it on both sides. Why? Because now you put it above, means on this side, and that's why they're also doing it on this side. Okay, so this is the length, that's the pitch. The weld size hasn't even been specified yet. Okay, now if you want them to stagger the welds from one side to the other, you notice that the two little triangles are staggered. Okay, so in other words, this is a 3-inch segment staggered at every 10 inches. Okay, and what happens is that from here to here, you'll have from this side to this side, this will be put at 5 inches. Then on the same side, there'll be a 10-inch distance between the centers, and so on. Okay, so therefore, this means that you want to stagger. You don't want them to be back to back. You want them to be staggered. So, and that's, you know, so just to show you how, you know, how people are going to interpret the information. Okay, and of course now, so here you have, for example, this is the size of the weld, this is the length of the segment, this is the pitch between each segment, okay? So 50, 150, 50, 150. And of course here, I think I took the same numbers anyway. So this is how you would do it in, okay, so this here, like I said, in this case here, they haven't provided the size of the weld will go here. So in other words, this can be either 3/16 weld, 1/4, 5/16, and so on and so on. So here you put the size of the weld, here you put the length of the weld segment, and here you put the distance or the pitch between each weld segment. And if you omit, okay, if you omit this, okay, then they're going to just make a 50 millimeter length weld for you, okay? Okay, so now, and then of course here's the same thing. In other words, 12 millimeters, 12 millimeters, so you want the same size of weld on both sides. You have an 80 millimeter length, which is basically 3 inches, and you want, so this is how you would specify it in metric. So as far as the numbers go, one is in metric, the other one's in imperial, but as far as the symbols go, they are all the same. Like in other words, fillet, fillet, okay? Both sides, okay? Length, length, okay? Pitch, pitch, okay? So in other words, this stays always the same, like I said. And very rarely do people, like I never really bother with the specifications because I leave that to the I just specify the strength of the electrode, okay? I do not specify the anything else. I just specify what strength the electrode has to have, and that's it. So that should give you an idea of how, you know, like how to specify a weld on a drawing. Okay, now guys, you don't have to memorize this. You can come back to this and look at them and make sure you follow these instructions very carefully, because you don't want to put the wrong symbol and even at the wrong location. Like I'm trying to stress here is that even whether it's above or below has a significance when it comes to weld symbols. Okay, so below means where you're pointing. And then, of course, for example, if I was pointing on this side here, if I was pointing on this side here and I wanted the welds to all happen on the other side because it's clear on my drawing to point on that side, then all this information would simply be going on top, okay? I should do it the other way, sorry. I should do it, okay? Let me erase. Okay. So if I wanted to have this here, I would show this on top here. So, you know, put in the, anyway, I should have drawn that the other way. I apologize. And therefore I would put the information here in the weld, okay? So that's how you keep that in mind, okay? Even on which side you indicate the information tells the guy on which side you want that information to be performed. So that's, like I said, it's, now, I also want you to realize, okay, when we're talking about weld, okay, welding is also defined by how the weld is going to be performed, okay? And of course, for example, here you might hear somebody saying it's a flat position. In other words, these two pieces are laying on a table, okay? And therefore the guy puts them back to back and he's just welding, flat and so on. Okay, so this is a very simple and, you know, very inexpensive way of doing things. Now, this is an overhead weld. Okay, so overhead welds you can perform overhead welds, but they are very expensive to perform. Okay, so in other words, when the welder has to perform a weld that's over his head, okay, it is a very expensive. It's more expensive than this. Okay, and then of course you've got the horizontal. Okay, which is, you know, it's, and then you got the vertical. So this is, okay, so this is something that you might hear, you know, this is an overhead weld. Well, because it's where the weld is being performed with respect to the welder. It's going to be over his head. Flat means it's going to be like below his hand. You know, horizontal means it's just going to go straight across, and vertical up and down. And like I said, so if you hear this, okay, these are what you're actually going to should be able to visualize. It's flat, horizontal, vertical, or overhead. So, and I want you to appreciate when you hear overhead, what it means, okay? So you'll hear that sometimes. That's just so you can learn some terminology or some glossary. Now, here is something you guys should realize, okay? We'll talk about fillet weld. Like I said, it's the most common weld that we use to connect two pieces together in structural steel. And therefore, you might as well learn the different terminology of a fillet weld, okay? So here, for example, they're trying to show you that these are two fillet welds, okay? But the size of the weld is determined by this distance here, what they call the throat, okay? So that's how you determine the size of the weld, okay? It's the throat here. So therefore, you can appreciate that when it's convex, okay, it goes from there to there. It doesn't go from there to there. It goes from there to there. And then here, where it's concave, it goes from there to there, okay? So that's one thing you should keep. So the effective throat size determines exactly the strength of the weld, okay? Now, the weld size is determined by the leg, okay? So in other words, okay, so basically the weld size would go from, okay, so the leg, so when we say a 6 millimeter weld, that means that this will have to be at least 6 millimeters. We say 8 millimeters, and this would have to be at least, so that's the weld, the leg, and the size are defined. Okay, that's how you define a weld, by the size of the leg. And of course, okay, so this is, so you can appreciate when they're talking about throat, okay, because guys, look what happens. Okay, I don't know if you guys can appreciate this, but when you're welding, like for example, this is one piece here, right? And this is another piece here. And what you're actually doing is you're trying to connect these two pieces by joining it where this angle is here, okay? When you're welding, okay, what you're actually doing is that you are melting the steel, and you're actually letting the steel refuse together, and they bond together. So that's what you're actually doing, okay? You're actually melting the steel. That's what arc welding is all about. The electricity is so high that it can actually melt the steel, and then the flux in the electrode actually allows this thing to be, okay? So basically, when you look at a weld, okay, if you look at this, you ask yourself, well, where is the resistance of the weld? Well, one resistance is the weld itself, okay? And therefore the weld has this here that it can resist. In other words, it can break right across there. That's one of the resistance of this welded part. And the other one is what they call the base material. In other words, what can happen is, let me just change the color, is that the material here can break off. Okay, so there's two things you have to worry about a weld. Is it going to be the weld that's going to break, or is it going to be the base material that's going to shear off? Okay, and that's something you have to check when you're checking your weld capacities. Okay, so excuse me. So this is what we're going to be doing. Okay, we're going to be checking both the weld and the base material. And then what they're saying is that if the electrode that you're using, the electrode is a little rod that you see the guy adds to his welding gun, you understand? If the electrode is a match for the material, you don't have to necessarily check this, but I like to check it anyways, and we're going to be doing an example. So that's something new that came into the standard, that you don't have to check the base material anymore if you're using matching electrodes. But when do you know? I'll show you which are matching electrodes, but I would always double check it just to make sure. Okay, so like I said, these are the three parts of a weld, of a fillet weld, that you should be able to visualize. Okay, the throat is this part here, the leg, okay, and the size. Okay, so this is the leg here. It goes from there to there. But then in this case here, you notice that the size is much smaller than the leg. Okay, so in other words, even if this leg here, so therefore this would, if somebody says this is an 8 millimeter weld, well, it isn't 8 millimeters because the size would be much smaller. Okay, so even though this leg is 8 millimeters, the only time it would be an 8 millimeter leg is when it's convex like this, and therefore from there to there, and then this would become also the size and the leg are one. Okay, so if it's a concave, be careful. If it's convex, well, you can rest assured that the leg that you specified would also be the size of the leg. That's what they're trying to make you show here. Now, if ever you want to, I'm trying to remember, if ever you want to measure a weld, well, they've got these nice little instruments, okay, that actually go in, okay, and there's a meter here. When touching the face of the weld, the digital scale reveals the actual distance from the root of the weld to the face, which is the actual weld throat length, okay, because it is a throat length that's going to be the resistance, and therefore that's how the guy that goes on the site or in the shop, if he wants to check that he's got the right size, he brings his instrument with him, and he makes sure that all across that weld, okay, I mean, like he can basically look at where he sees where there's depressions, and he would only measure there, and then he would see make sure that that throat has the width that is required in order to meet the welding resistance that you specified. Okay, so that's and I find that it's a nice little instrument to have, but I don't. Okay. Now, these are the common weld sizes. Okay. So in other words, here you have the imperial ones. Okay. So when you're going to be specifying a weld size in imperial, you start with 3/16, and you'll notice that it jumps up by a 16th. In other words, this is 4/16, 5/16, 6/16, 7/16, half an inch. Okay, then it jumps up by, after that, it jumps up by 1/8 of an inch. Okay, so from 3/16 to a half inch, the increments are by a 16th of an inch. And then after that, by 1/8 of an inch. So you shouldn't be specifying 9/16. You understand? It's either a half or 5/8. Okay, now that's imperial. Okay, now in metric, of course, you got 5, 6, 8, 10, 12. So here they jump up basically, so here they jump up by 1, and then after that they jump up by multiples of 2. Okay, and then once, okay, so they jump up by multiples of 2, which is nice. Okay, but remember in imperial, from 3/16 up to half an inch, you have multiples of a 16th, and after that they're multiples of 1/8. That's something like you wouldn't be specifying, how can I say, you wouldn't be specifying 9/16. It's either half an inch or you use 5/8 of an inch, and so on. So these are how you specify your weld size, and of course each one is going to have a certain resistance, and that's why you, okay. So these are your weld sizes. Now, here is something I want you guys to keep in mind. Okay, this here is just good welding practice. Okay, this is good welding practice so that you can keep in mind that, and we're going to be using this in one or two of the examples. And so here, what they're saying is when you're doing a fillet weld, okay, the minimum size of a fillet weld as measured through should not be less than the value shown at the right. Okay, except that it not exceed the thickness of the thinner part. Okay, so here what they're saying is that if my material thickness is up to 6 millimeters, okay, I should not use anything less than a 3 millimeter weld, minimum. Okay, if the material thickness is between 6 and 12 millimeters, I shouldn't be using anything less than a 5 millimeter weld. Okay, this is minimum weld thickness. And then from 12 to 20, in other words, from about ½ inch to about 3/4 of an inch, I shouldn't be using anything less than a 1/4 of an inch. This is in the old days. Okay, 6 millimeter weld. And if I'm welding anything where the material thickness is greater than 20 millimeters, I shouldn't be using anything less than 8 millimeters. Now, keep in mind what they're saying here is that if I have for example, if my leg here, if the leg of my angle here, okay, if this leg here happens to be, 9.5 millimeters, okay, and the gusset plate happens to be 6 millimeters. Well, you always go with the smallest thickness to determine what size of weld you should be using, okay? So for example, that's why you try to make sure that, for example, here they say, except that it need not exceed the thickness of the thinner part. Okay, so for example, I have a 9 millimeter weld, I have 6 millimeters here. So therefore I would specify nothing less than a 6 millimeter weld here. That's what they're saying. Okay, so think of if the both two thicknesses are the same, well, these are the minimum weld that you're using. If the thinner part has a smaller thing, then you should not exceed the thickness of the smaller one. Okay, that's one thing. Okay, so that's what they're trying to make you say here. Okay, the minimum effective length of the weld should be 38 millimeters or 4 times the weld size. Okay, so in other words, when I'm welding, okay, if I, for example, and this is going to be applicable when we're going to be doing the connection of our vertical braces, okay, if all of a sudden I have here, okay, I do my calculations and I see that I need only 25 millimeters of weld. Well, they're saying that even though you only need 25, it should not be less than 38, okay? Or 4 times the thickness, the greater of the two. Okay, so in other words, if I'm using a 12 millimeter weld times 4, it should be at least 48 millimeters. Okay, and it's either a minimum of 38 or 4 times the weld size. So keep that in mind. So even if you do your calculation theoretically, you end up saying, oh, I only need 19 millimeters. Well, you don't put 19 millimeters. You put at least 38 or 4 times the weld size. That is something you need to do, okay? So keep that in mind, and this is just good welding practice, okay? Now, the maximum fillet size, okay, there's a minimum and then of course there's a maximum, okay? So recommended for good practice along the sheared edge, okay? So here we say D max is equal to T. So in other words, when you have 6 millimeters, less than 6 millimeters, okay, the maximum thickness that you should use should be the thickness of your material. Nothing, you can't, for example, if I have a 5 millimeter plate, don't use a 6 millimeter weld, use a 5 millimeter weld and so on, okay? So that's what they're trying to say here, okay? Now, when you're going over 6 millimeters or above, okay, your D max should be T minus 2, okay? So in other words, you should always use, for example, if I'm going to be using a 10 millimeter plate, I should be using an 8 millimeter weld. 12 millimeter plate, a 10 millimeter. So in other words, use a D max of T minus 2, okay? That is the size of the weld. So D represents the size of the weld, and that's something we'll apply when we're doing our problems, okay? So that's here, okay? So these here are minimums and here are maximums, okay? Now, there's also when you are welding, for example, here, okay? I don't know if you guys can understand these sketches, but to me, okay, so for example, this here happens to be, okay, this here happens to be a steel angle, you understand? Whereby you have that little fillet that's caused by the rolling of the steel angle, okay? And what they're trying to show you here is that when you have a fillet in here and you're welding it this way, okay, well, in reality, whatever D you use in your calculation, you should remove it, you should reduce it by this much. That would be the effective size, because you might not be able to get the weld in there because of this little fillet, okay? So that's something you should keep in mind. And then if all of a sudden, this is my steel angle here like this, and I'm welding it to a plate here, because of this fillet here, okay, the maximum size of weld I should be specifying is 75 times the thickness of the whatever you want to call it, of the leg or of the element, you understand? So if I have, for example, if I happen to have, I'm trying to weld a wide flange to a plate here like this, okay, well, that's what this looks like, and therefore I got to keep this in mind for that thickness there. And if I'm going to be, connecting an angle to some kind of a plate here, they say that you take the thickness of the leg here, and the D size should be less than 0.75 of the thickness of the leg. So keep that in mind, okay? So when the fillet weld are used in holes or slots, the diameter of the hole, okay? Now, that is something we will be applying when we're going to be doing our double angle connections and all that, okay? So this is something I'll come back to, and this is where the information comes from, okay? So this is just good practice. Now, here is another thing you should keep in mind, okay? If ever you are creating what they call a lap joint, in other words, I have a piece here like this, okay? And then I have another piece here like this, okay? So I'm lapping these two together, okay? And of course, I'm going to be welding here, and I'm going to be welding on the underside here, okay? What they're saying here is that the L minimum here, okay, should be 5 times T1. So they don't recommend that you make the length of your lap less than 5 times the thickness. Okay, and that's when T1 is less than T2. So in other words, you take these, you take the thinner, if they both have the same thickness, then it's just 5 times the thickness, but you take 5 times the smaller thickness, and that should be the minimum lap you should put, okay? So if I'm using a 6 millimeter plate, okay, and here I'm using an 8 millimeter plate, well, what they're saying here is that when you're lapping these together, don't make this less than 30 millimeters. That's what they're suggesting. In other words, that's good practice. Now you make it 30, 35, 40, whatever you want, but don't make it less than 30 when you're lapping these two pieces together, okay? And so that's another thing you should keep in mind. So this is just information that's going to, give you good practice of how to specify things. Oh, okay. So this is just like I said, we will be applying this, because we are going to be using double angle connections, okay, and we're going to be specifying, making sure our D does not exceed 0.75, the thickness of our angle here, and so on. And remember, if you're doing it the other way around, then whatever D you specified here in your calculation, remember that the effective is really, you take away 1/4 of that D when you're doing your calculations. That's all they're saying there. Any questions before I move on? I can go back. Now's the time to ask. So this is just some very general information regarding welding. You're starting to, this is probably the first time you've ever been exposed to welding symbols. I don't know, maybe it's the first time you've ever been exposed to welding and so on. Does anybody have any questions before I move on? Is something not clear? Now's the time to ask.
I think it's okay.
It's okay? Okay. So if it's okay, we'll move on. And okay. Now, how do we apply all this? Okay, so basically what we need to do is know how much resistance does a weld give, okay? And of course, the factored resistance for direct shear or tension or compression induced shears shall be taken as, okay? So this is the equation to calculate VR for a weld. Okay, it looks complicated, but like I said, I'm going to give you the equation. I think we're going to use the equation once, and then from there on, we're going to always use the tables. But I wanted to show you the equation, okay? So this is the equation, okay? Now, this part becomes a little tricky. I lose a lot of people when we talk about this part of the equation, but one thing at a time, okay? So as any equation that you have in limit state design, right, there's always a reduction factor. And here, of course, the reduction factor for welding, okay, is 0.67. So therefore, if ever using this equation, just put 0.67, square it, and you'll take care of these two things right away. AW is the area of the weld. Now, be careful, okay? If this is the element that I have here, and this is the element that I have here, okay? And this is the weld that I'm putting here, right? Well, the area of the weld, okay, is what? The area of the weld is this length here, that length there, multiplied by by the total length of the weld. That is the area of the weld. In other words, okay, so that is AW. It's not this length here, it's the length of the throat. Okay, that's what you have to remember. And XU is the resistance of the electrode. Everybody know what an electrode is? I should have maybe went to get an electrode on YouTube. The electrode, I don't know if you guys know, like when you're welding something, you got your little gun here like this, that's connected to a wire. This is arc welding. And then after that, there's these little rods here that the guy puts in his gun here. And then this kind of all melts away as he's welding. You guys seen this, the electrodes for welding? Yes, no, maybe. Well, for those of you that don't know what electrodes are, I do suggest you go on Google, just put electrodes for welding, and you're going to see a whole bunch of them. I should have brought one up. I apologize. Now, AW is the area of the effective weld throat. Okay, that's what I was showing you before. And XU is the ultimate strength of the electrical classification number. And now, theta. Okay, let's talk about theta. So this is theta here, okay? Theta in degrees of axis of weld segment with respect to the line of action of applied forces. Okay, so what does this mean? Okay, now here is my element, and it's being pulled. Okay, and this is where it's being welded to here. Okay, so now I have a weld segment here. I have a weld segment there, and I have a weld segment there, right? So read what it says here. Angle in degrees of the axis of the weld segment with respect to the line of action. Which one is the line of action? This is this is how the member is being pulled. So where is the line of action? In the direction of the force. Everybody understands that? Now, what's the angle between here and the line of action? For this segment here and for this segment here, what's the angle between this segment and the line of action? Can somebody tell me?
Since it's parallel, it's 0.
It's 0. Okay, so the line of action here gives me an angle of 0. And for this one here, what's the angle of this segment here with respect to the line of action?
90.
90 degrees. Okay, so that's what they're trying to make you understand. You have to look at, because when the line of action with respect to the weld, here what happens is that, so you guys can appreciate it, that here the weld is acting completely in shear. Completely in shear, therefore it has one resistance. Here the weld is acting in shear and in tension, therefore it's got a slightly higher resistance. So depending on how the line of action is acting on the weld, it can have a different resistance. That's why, okay, so that's what they mean by the line of action. Okay, now MU, the strength reduction factor for multiple orientation, okay? Okay, for a single weld, MU is 1. Okay, so in other words, if you happen to have just one weld, well, this goes to 1. But when you have a group of welds, okay, for example, I have here, this here is my element. Here's one segment in this direction. Here's another in this direction. Here's one in this direction. Or I can even have, for example, it can be like this. Doesn't matter if it's at an angle. I don't care if it's straight. And so as long as I have one segment that's in a different orientation than in another segment, okay, this is called a okay. This is called for the groups, okay, and therefore I have to worry about the MW. Okay, so and I'll show you how to calculate the MW for these two situations. Okay, so that's something you have to keep in mind. For a weld group of multi-orientation, you have to reduce the overall effect of that group. And that's what this does. Now, so for joints with multiple weld orientations for each segment. So now here, this is very complicated, okay? I mean complicated. This is where I lose a lot of people because they don't see this theta 1. This theta 1 here and this theta 2, I want you to realize one thing. It's got nothing to do with this. This is the orientation of the weld segment, okay? So that's got nothing to do with this theta, and these are totally different thetas, okay? They might have the same value, but they are totally different thetas. Now, so theta 1 is orientation of the weld segment under consideration. In other words, if I'm trying to calculate, if this here is what I am welding, okay, and all of a sudden this here, okay, and that's the weld segment that I'm under consideration. Well, I have to look at that segment with respect to theta 1 is the angle with respect to what I'm considering. Okay, so I don't know what it is. I'd have to look at that. And then theta 2 is the orientation of the weld segment in the joint that is nearest to 90 degrees. So here, for example, okay, I would happen to have a weld here, right? So what happens here? This is my line of action, like this. Which weld segment is nearest to 90 degrees? Well, this one is at 90 degrees. Therefore, my theta 2 value would be 90 degrees, okay? And my theta 1 is the orientation with under consideration. So therefore, in this case here, this would be theta 1 for this weld segment. This is theta 1 for this weld segment. And this is theta 2 for this weld segment, okay? And you'll see how this is applied to a thing, but I know everybody gets lost with this. They don't realize, they don't see the line of action. They don't look at the orientation of the weld group of the segments, and that's why it gets a little confusing. So if you start visualizing how the welds are being placed, and that's what's really is going to determine these two values and this value here. So in other words, how they're being placed with respect here to the line of action, and then of course for the group that you're calculating the resistance for. So this is all the variables that you have in here, okay? Now, on top of that, you also have where overmatched electrodes are used. In other words, where the electrodes are stronger than the base material. The base material capacity at the fusion face shall be checked and may be considered to have the following strength. So now, the first equation, okay, so if this is what I'm welding to this, okay, and this is my, okay, the equation on the other page calculated the resistance of the weld right here. That's what we saw on the other page. This equation here will calculate the resistance of the weld right here along the face that's being fused together. So in other words, it's going to calculate the value there. And the reason why you don't calculate it here, because it's only as strong as one face. And that's what this does. It calculates the VR right where the metal is being fused together. Okay, and that's what this equation does. So the one from the before was for the weld, and this is for the base material. Like I said, now they came up with this thing that if you're using matchmaking electrodes, you don't have to check this anymore. But in the old days, we had to check it. And if ever you're using overmatch, in other words, if the electrode is much stronger than your base material, you'd have to check this to see which one governs your design. So keep that in mind. Now, same value, phi W 0.67. AM, of course, is the area of the metal that's being fused together. In other words, it would be the length of your leg times the height of your leg times the length of the weld. And FU, of course, is the ultimate strength of the base material. So in other words, the FU that you've been using before. So the shear area of the fusion face, the least ultimate tensile strength of the joint, okay, which like if you're using either 300 or 350 MPa steel, the FU is 450 for both those types of steel. In other words, the ultimate tensile strength is minimum is 450 megapascals. Now, so those are the equations. Now, this is, of course, okay, these here are the strength of the electrodes. Okay, this is the strength of the electrode. Now, this 49, in our days, I used to have E70. Okay, E70 means that this electrode has a strength of 70 KSI, kips per square inch. Well, we're no longer in imperial. This E49 stands for an XU there, that XU value in the equation of 490 megapascals. Okay, that's what the E49 stands for. So this is the strength of the electrode. Okay, in other words, how much the resistance that flux or that has. Now, this is the most common. Okay, so in other words, this is the most common one that we use for clear all drawing. Okay, so this here is the most common one that we use. And of course, if you look here, this is the grades of steel that you can use for that type of electrode. And in theory, what they're saying is that since you're using this electrode with these grades of steel, in theory, you don't have to check for the base material because this is a matching electrode for this steel. And I'll show you that it's true. Now, the E430 here, the E43XX, XX is for very specific. Remember that specification that you had in the back? Well, I always leave that to the welder to decide which one he has to use and what temperature and so on and so on. All I want to make sure is that whatever he's using has a resistance of at least 490 megapascals. That's what I care for as a structural engineer. And for him to get the results that I'm asking for, I let him worry about what he has to use here. Now, you notice here for the weaker electrodes, so it's made for the weaker strength of steels. A36, A36, okay, these are weaker strengths of steels. Okay, so we don't use, very rarely do you use that, but if you're using a very like A36 steel, which is a very weak steel, remember you should be using an E43 if you want to match the electrode. If you're using this strength of steel to weld that, then you have to check the base material. That's what they're basically saying. And you can get into higher. These are overstrength electrodes. So in other words, this one has a strength of 550 MPa, 620 MPa, 820 MPa. So you can get into some, and then of course this is made for some really high strength steels, okay, and so on. Now this is the, okay, so this table tells you, okay, tells you the strength of the electrode, okay, and then of course this is based on the area of the weld. It tells you, for example, 5.67 XU. In other words, these three values multiplied together, you're already down to 220, okay. And then when you want to actually take the per millimeter of the throat, you're down to this. That's all this is. But we're never going to use this, okay. This is just to show you the different strength of electrodes that you have, okay, and for which steel that you're going to be matching them with, so that you don't have to check the base material if you don't want to check it, but it's good to check it anyways. And of course, okay, so this is the welding material, this is the base material, and if you use the right welding material with the right base material, you don't have to check the, okay, you don't have to check the base resistance, but we'll do it at least once, so this way you'll know what I'm talking about. And like I said, what we're really interested in is this. This is what we're interested in, okay? Because this gives us the value of the size of the weld per millimeter of weld, okay? Millimeter of weld, okay? So remember, so here what we're doing is, okay, 5, 6, 7, 5, 6, 8, 10, 12. Like these were the sizes that I showed you in the previous slide. And of course, this is the imperial sizes here, okay? Now, angle between welding axis and action of force. So that's that value of theta that we have in that equation, okay? So that's the value of theta. So basically what they're saying is that if I happen to have a piece of weld here that's welded here and welded here, and my line of action is this way, well, theta here is 0. So therefore I would, for this weld segment here and this weld segment here, I would only use the values under this column. Now, if I happen to have a weld segment here on this side also, okay, well, this one here is at 90 degrees. Therefore, when I want to go calculate the resistance of that segment, well, I'm allowed to use this column here. And if whatever angle I have in between, for example, if all of a sudden my piece is cut at an angle here like this, okay, and I have a weld segment there, and I have a weld segment there, and I have a weld segment there, well, as long as I can determine what the angle is in here, then I can go and take advantage that some of that weld will be in tension and it will be slightly stronger, okay. Now, you'll notice here, what I like about this table, okay, you'll notice that at one point, the values stay exactly the same, okay. It doesn't change. And that's because what this table does, make sure that the base material is what governs the welding resistance, and avoids you from making that mistake of oversizing the welds from the equation. That's what I like about this table. If you don't realize that your base material governs and you don't check that and you take the equation and you put 90 degrees, you will over evaluate the resistance of your connection. So that's what I like about the table. And that's why I like you guys to use the tables. It has some safeguards built into it that you might not realize. So, okay, so we are going to be using this table, okay, and like I said, this is the table that we'll constantly be coming back to and determining what size of weld we want, like what's the resistance to weld, and so on and so on. So, and like I said, so what this table does is it takes this whole equation here, okay, it takes this whole equation here, okay, and it also takes this into consideration, the base material, takes both of these into consideration and gives you the value depending on the size of the weld. It tells you what's the resistance in kilonewtons per millimeter of weld, okay? And guys, I hope you appreciate it. Millimeter is not very wide, okay? Not very long, I should say. So this is what it does. It takes this equation or this equation. You see the or here? And what the table does is that when this one governs, right after this angle here, this is the one that governs, and therefore it limits it to that value there. And then after that, okay. And then after that, if it's not the base material that governs, then this is all the values you have in here. So the table makes it a little bit easier for you to do this calculation. Now we're going to do one, I think, I'm not mistaken, I'm going to do one that's at least, okay, so here. I'm going to throw one at you that has an angle and all that. So therefore, when we do something at 90 degrees, okay, we're going to be a little bit easier and all that. So I'll throw you one that's at 90 degrees here, okay? So here, what we're going to do is we are going to, okay, so in the well configuration shown in figure 8, oh yeah, in the figure, okay, 8mm fillet welds are used. Okay, so that means that, okay, that means that the leg here of this fillet weld is 8mm. Okay, so right here, right in there, the vertical leg and the horizontal leg is 8mm, and of course the resistance of the weld itself is not the length of the weld. The resistance of the weld and is actually the, oops, sorry, is actually the throat. The resistance of the weld is based on that length there, not that one. Okay, because that's where it can shear off, because that's where the two pieces are being met together, and that's where it can shear off. Now, determine the factor tensile resistance TF of the weld group can resist. In other words, how much resistance can these three segments produce so that we can determine how much we can apply to here, okay? So let's go ahead and do that. So first of all, okay, so we go back. So here's the equation, right? Here's the equation that we're going to be using, and we'll do it once with the equation so you guys can see it with the equation. And then after that, we'll do it with the table. So at least you'll have, you'll be exposed to both ways, okay? So here's the equation, very ugly equation, I know, but so here we go. So now what is the, so basically the well segment at 60 degrees. Well, here, what I have to do is I have to consider all the well segments that are in one orientation, all the well segments that are in another orientation because of this value of MW here, okay? So I'm just going to be calculating the resistance of this little segment here first, and then after that, I'll calculate the resistance of this segment because these two are in the same orientation. So the orientation of the well segment under consideration, theta 1 is 60 degrees. That's the one I'm considering. So therefore, theta 1 is always a well segment I'm considering, okay? Now, theta 2 is the segment that is closest to, okay, the orientation of the well segment that is nearest to 90 degrees. So in this case here, theta 2 is what? Which one is nearest to 90 degrees? So therefore, this is the angle nearest to 90 degrees. Therefore, theta 2 is 60 degrees. Okay? So that this becomes my theta 1. This becomes my theta 2 in calculating this value here of MW.
Sir,
Yes.
just for theta 1, can you re-explain how we got that 60? Because
How did I get what? For theta, no, theta 1 is the well, look, orientation of the weld segment under consideration. I'm trying to calculate the resistance of this weld here. I'm trying to calculate the resistance of this weld segment here.
okay.
Okay, so that's the one I'm considering. So what's the angle of that weld? With respect to the line of action.
Okay,
Pardon?
okay.
What's the angle
Yeah.
of this weld with respect to the line of action?
60.
60. So that becomes theta 1. Okay.
Okay.
Okay. Now, which weld segment is closest to 90 degrees?
Also the 60.
It's also 60. See? So in other words, here what I'm saying is that this theta 2 is 60, and this will always be theta 2 for this problem. But the theta 1
Okay.
changes depending on the well segment I'm considering. Okay, now I did this for academic reasons, but to show you that when the well segment under consideration is the same as the well segment that is close to 90 degrees, then the value of MW ends up being 1.0. I did this purely for academic reasons because this value here is the same as that value there, and therefore the MW only for this well segment here is equal to 1.0. Okay, so that's just for that one well segment. Now, once I've got that, okay, and all that, now what I need to do is I've got everything I need in here to be able to do this calculation, okay? So now for the well segment where theta is equal to 0, okay, in other words, the ones that are horizontal, the ones that are parallel to the line of action, okay? Well, the theta 2 always stays 60 degrees. Now the MW is going to change, okay? So for those two weld groups, for those two segments, I should say, the MW drops down to 0.895 because this here is 0 degrees. This here stays, theta 2 stays the same for all. Once you determine which is theta 2, in other words, which is a weld segment that is nearest to 90 degrees, that always stays theta 2. So for that, for those two segments here, when I'm calculating the resistance of those two welds here, then I'm going to have to add, I'm going to have to multiply the value of those two by 0.95 in the equation. So that's that. Now, the longitudinal weld theta is equal to 0. Okay, now for the welding resistance, here's my equation. I've already calculated the values of MW for both orientations. Okay, now, so therefore, it's just a question like here. I want you to realize this is, okay, this is the value, this is the size of weld. Now, what I can either use here the cos of 45 degrees or I can use the sine of 45 degrees. Why do I do that? Because if you remember from your trigonometry, okay, what is the length of that member? Well, if this is 8 millimeters, this here is either the sine or the cosine of 45 degrees, if you remember that, okay? So that's what this is. It gives me the length of the throat here. That's why I put 45 degrees. You could use the sine of 45. I hope you realize the sine of 45 and the cos of 45 is 0.707. They have exactly the same value. L is the length. So this gives me AW here. This is the AW value here. All of this for AW. Now, this is the strength of the electrode, 490 megapascals, which is 0.49 kilonewtons per millimeter. In other words, I have 490 newtons per millimeter squared, and therefore, if I want to convert it to kilonewtons, I put 0.49 kilonewtons per millimeter squared, and that gives me the value of the electrode, XU. Now, this is for the orientation of the weld. Okay, so in other words, here it's 0, so therefore this goes to 1, right? It doesn't change anything. The sign of 0 is 1, and therefore this is pretty redundant, but this gets multiplied, and therefore I have the VR equal to 111 kilonewtons. So that's what the equation gives me. Now,
So I have a question again about the theta.
which one are you talking about? Are you talking about the theta here? Or are you talking about the theta 1 or the theta 2? Because when you say theta, in my mind, when you're saying theta, I go to this.
Yeah, it's theta 2.
Theta 2.
What? Yeah, when would it be 0?
Never.
Okay, that's what I thought. Okay.
If you have a weld group, never.
Makes sense.
Okay. If, in other words, if I only have it in one direction, right, then I don't have a weld group. It's only when I have weld segments in different orientations that I worry about MW.
Okay, got it.
Do you follow?
You.
Like, in other words, what I'm trying to make you understand is that if I'm only welding here and here, do I have a weld group? No. Both of these are acting in the same direction. Therefore, I don't have to worry about a weld group. Therefore, I don't even worry. MW becomes 1. The only time that I'm going to worry about MW is if all of a sudden I also have a weld here. Okay. Now, in this case here, this is my line of action. This becomes my theta 2. In other words, this is the weld segment that is closest to 90 degrees. As a matter of fact, it is 90 degrees. So theta 2 is a weld segment that is closest to 90 degrees or at 90 degrees. Okay. And then, so that's what they mean. So if the weld segments are all in one direction, you don't have an MW. If you happen to have weld segments at different directions, then you have to worry about MW. Okay. Now, so base material. So this is the equation for the base material. Now, of course, the base material, you have to remember 0.67, 0.67. Now, in this case here, is the height of the leg where the base material is being fused, 8 millimeters, okay, and 162. So therefore, it's not the base material that's going to be weaker. It is the weld itself. Therefore, it's the lower of the two. The VR is 111 kilonewtons. For the weld segment, that is at 90 degrees. And then after that, okay, for the weld segment at 60 degrees. Well, for the weld segment at 60 degrees, I use the same equation. The only difference is that this MW is 1, and I can take a value of 90 degrees in here, okay? So therefore, I do 0.67, 0.67, 8 millimeters, close to 45, 120 times 90, okay? And I multiplied by, and of course, this ends up being the sine of 1. This is 1.5 and so on. 60. I'm sorry, 60 degrees. I'm talking about 90 degrees, 60 degrees. And therefore, this gives me 209 for that one weld segment. And for the base material, I use this equation here. Now, here you see that the base material is weaker than the weld itself. So what they're saying here is that when I'm looking at that weld segment here, when I'm looking at this weld segment here, if I look at a cross section here, what they're saying is, okay, where the weld is being produced, okay, the fusion face here and the fusion face here, okay, are weaker than the weld itself, than this part here of the weld. So therefore, this is the one that governs the resistance. In other words, most likely the material is going to break off before the weld breaks. And that's what they're saying. And therefore, you take the smaller of the two. And it's not 209, it's 194. So, okay, now the resistance of the group itself, well, it's very simple. I have two that are in the 0 direction. I only have one that's in the 60-degree direction. Therefore, the VR of the total group is 416 kilonewtons. And that is using the equations. Now, what we're going to do is look at this with, okay, so that's the VR for the weld group. So VR has to be greater than TF. So as long as the force is less than 416 kilonewtons, you know that the weld group will be able to safely resist the weld. So make sure, if in other words, if you had a TF of 415 kilonewtons, that weld group would be sufficient to resist that force. Anything over 416, in theory, you haven't designed it properly. So that's with the equations, okay? Now, let me show you what we do this with the tables. Okay, we'll use the tables, so this way you'll see why I like the tables versus the equations, okay? The longitudinal weld at 0 degrees, okay? We go back to the table. Now, we said we had an 8 millimeter weld, and the orientation of the weld group is at 0 degrees. Therefore, the resistance per millimeter weld is 1.24 kilonewtons per millimeter. So therefore, all I got to do, this doesn't change. I've already showed you how you calculate the MW. That doesn't change. That stays the same. The only thing, I'm getting the values of this from the table themselves, and I know the length here is 100. So therefore, I have two welds. Each weld, an 8 millimeter weld at an orientation of 0 degrees would be 1.24 times the MW. That didn't change. That stays the same. And therefore, I get a total of 222 for those two weld segments. Now, for the weld at 60 degrees, I'm going to go back to slide 14, and here we go. So for example, I have an 8 millimeter weld, and the orientation is, well, here it doesn't make much of a difference. Between 50 and 90 degrees, it's exactly the same value, you see? So therefore, even though I have 60 degrees here, it would make absolutely no difference. And this is what I'm telling you, the table already takes into account this equation here. That's why it limits you what the resistance is. And therefore, I have 1.61. So I have 1.61 times L, and this stays the same. Therefore, I multiply these two together times 120, end up with 194. And of course, the sum of all the weld segments gives me the sum of the resistance of the weld group. And therefore, the sum of the resistance of the weld group, exactly the same that we got before. Okay, so guys, I prefer using the tables. Like I said, if you don't want to check the base material, you can sometimes overlook the fact that the orientation of your well can be stronger than the base material, and therefore you might have made slightly overestimated the VR value. Whereas in the table here, this made sure that when you use this value here, it was the base material that ended up giving you this value here and not the value of the weld itself. And that's what I like. And now we got exactly the same value. Now, I don't know if, I find that this is much easier. The only thing that you guys have to keep in mind is how to calculate that MW. And like I said, I'm going to repeat it one more time so that we can all, okay, we've got about 5 minutes to go. So for example, if I happen to have here, here's my angle here like this. Okay, this is my angle. And I happen to have whatever is being connected to here, okay? Whatever is being connected to. Now, here is, let's change colors, okay? Here is one weld. And I'm gonna put this weld in the same color because it's in the same orientation. And then I'm gonna change this color. I'm gonna put this as a blue here. Here's another weld. Now, this angle is being pulled this way. This is my TF. Does everybody understand what I'm doing?
Yes.
Oh, is everybody clear on what I'm doing? Okay.
Yes.
Now, for the MW, okay, the equation is, you remember the equation? Anyways, the hardest thing you have to remember in MW is what is theta 1 and what is theta 2. Okay? Now, look at this here, okay? Which weld group do you want to consider, the green one or the blue one? Which one do you want to first consider?
The green.
The green. Okay, so you want to consider, okay, so we're going to put 4, I'll even change color, green, okay? For the green, okay? Now, what is the angle of the weld group under consideration with respect to the line of action? What is the angle of the weld group with respect to the line of action?
0 degrees.
Therefore, that is theta 1. 0 degrees. In other words, theta 1 is the orientation of the weld group with respect to the line of action, 0 degrees. What is the weld segment that is closest to 90 degrees?
The blue one, no?
Exactly. And what is that angle?
90 degrees.
Exactly. So theta 2 becomes 90 degrees. So therefore, when I'm calculating MW for this group and this group, I use 0 degrees for theta 1, I use 90 degrees for theta 2. Okay, for those two. Now, for the blue one, what is the orientation of the weld segment with regards to the line of action?
$90.
That's right. So therefore, theta 1 becomes 90 degrees. And theta 2, does it change? No, theta 2 stays at 90 degrees. What happens when I divide 90 by 90? I get a 1, right? So for this weld segment here, the MW is going to be equal to 1.0, and for these, it's going to become slightly smaller than 1. And that's what, and then you use that equation to calculate the MW. Do you want me to repeat it again? So guys,
No, it's okay, sir.
Pardon?
No, it's okay.
It's okay. I know it was like guys, read the wording and just keep the wording in your mind. What is the orientation of the segment with respect to the line of action? Theta 1. which is the line segment that is closest to the line of action? Theta 2. And in this case here, here's my line of action. And the one that's closest to 90 degrees, as a matter of fact, it is 90 degrees. This becomes my theta 2. And theta 2 stays the same for, so for example, if I would have a very bizarre, I don't know, like let's do something that is non-academic, which is very unrealistic. I have this, I have this, I have this, I have this, okay? And all of a sudden I decide to put a weld here, 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 and here, okay? Let's say that that's my weld. In other words, like, so for example, I had an angle here, an angle there, a different angle, and, or, okay, let's here. I have an angle here, I have an angle there, I have an angle there. This one here is 45 degrees for some reason. This one here is 60 degrees for some reason, and so on. Okay, and I decide to, and all of a sudden I decide to put a weld in here. I should have changed color. I decide to put a weld in here, a weld in here, a weld in here, and a weld in here, and this thing's being pulled like this. Everybody follows? Okay, so therefore, what you have to look at is, out of all these angles, which one is the closest to 90 degrees, to the line of action? Which weld segment is which is the angle of the weld segment that is closest to 90 degrees?
Bottom right, no, the 60 degrees.
This 60 degrees, so therefore this becomes your theta 2. So theta 2 stays the same for all your weld segments, okay? So for this weld segment here, when you're calculating this one here, your theta 1 is 60 degrees, and your theta 2 is 60 degrees. For this weld segment here, your theta 1 is 0 degrees, and your theta 2 is 60 degrees. For this segment here, your theta 1 is 45 degrees, and your theta 2 is 60 degrees. You understand? So you just have to remember, once you've established theta 2, in other words, which is the segment that is closest to 90 degrees with respect to the line of action, that stays your theta 2 for the whole weld group. And the theta 1 is the angle of the weld with respect to your line of action. So here, the line of action is at 0 degrees, here it's at 45 degrees, and here it's at 60 degrees. And this is 0 degrees, okay? And that's all you have to keep in mind. And like I said, guys, first, I lose everybody on this topic every year, okay? Or every second year, I should say. And hopefully, you know, like when you do it a couple of times, it can become a little clearer. But you have to read the wording, try to understand the wording, try to visualize it, and that's when it's going to click, and you're going to have that aha moment. Aha, you know, guys. When I saw this the first time, I said, what the hell are you doing to me now? Because this is all new. Okay, this is a completely new way. Before we didn't have to worry about this. Now they've taken that, they've thrown this into the equation. Okay, so guys, do assignment number 6 for next week. It should be popping up on Leah sometime within the next, or should already be there. I think I put it for 9:30. And I think that's it. So what we'll do is we'll break till 10 o'clock. We'll come back. Today's lab shouldn't be that long, okay? Hopefully you guys will, you know, the lab, we're gonna be doing the vertical braces of the lab. It shouldn't be that long, and we'll be back by 10. Sounds good to everybody? I'm sorry I went a little overboard today in the lecture, but and come back to this meeting here. I'm just going to stop this recording, and then I'll record the lab on the next. So end. Okay, so let me stop recording. Okay.